The topic of this lecture is Important Theorem Part 2 of Complex Analysis. We'll cover these points in this lecture: harmonic function, harmonic conjugate, ML inequality, example, and Cauchy integral formula. So let us start with harmonic function. A real valued function hxy of two variables x and y is called harmonic in a given domain D of xy plane if h has continuous partial derivative of first and second order in D and satisfy partial differential equation hxx xy plus hyy xy is equal to 0, which is called Laplace equation. In this case, hxy is called harmonic function. Now let us see a theorem. The statement of this theorem is, if a function fz, which is uxy plus ivxy, is analytic in a domain D, then its component function u and v are harmonic in D. So we have to prove if fz is analytic, then component function u and v are harmonic in D. So let us see the proof. Let fz is equal to uxy plus ivxy be analytic in D, then its real and imaginary components uxy and vxy have continuous partial derivatives of all order in D and satisfy CR equation. What is CR equation? Ux is equal to Vy and Uy is equal to minus Vx. This is because fz is analytic. Now, differentiating both sides with respect to x, we get uxx is equal to vyx and uyx is equal to minus vx. Again, differentiating both sides with respect to y, we obtain that uxy is equal to vyy and uyy is equal to minus vx. Also, continuity of partial derivatives of u and v implies that uxy is equal to uyx and vxy is equal to vyx. Then by 2 and 3, this is 2 and this is 3, 2 and 3, we have that uxx is equal to vyx and vyx is same as vxy and vxy is minus uyy. But from this, we obtain that uxx plus uyy is equal to 0, which implies u is harmonic function. Similarly, from 2 and 3, we obtain that vxx is equal to minus uyx, which is same as minus uxy and which is equal to minus vyy. So this implies vxx plus vyy is equal to 0. This implies that u and v are harmonic in D. Now let us see what is meant by harmonic conjugate. That u and v are two harmonic functions in a domain D. If first order partial derivative of u and v satisfies CR equation, ux is equal to vy and uy is equal to minus vx. In this case, if these conditions are satisfied, then v is called a harmonic conjugate of u. Now let us see a theorem. This theorem says the statement is, if fz is equal to uxy plus ivxy is analytic in a domain D, this if and only if v is a harmonic conjugate of u. So we have to prove, okay, if u fz is equal to ux plus ivx is analytic in domain D, if and only if v is harmonic conjugate of u. So let us see the proof. If suppose v is harmonic conjugate of u, then by the definition, this definition, ux is equal to vy and uy is equal to minus vx, that is CR equations are satisfied and first order partial derivatives are continuous in D. But this implies that f dash z exists in D for all points by sufficient condition of differentiability. Therefore, we conclude that fz is equal to uxy plus ivx is analytic in D. This is by definition. Now conversely, let fz is equal to uxy plus ivxy is analytic in D. So this is our supposition. Then u and v are harmonic in D, as we have seen in the last slide, and as fz is analytic, so this satisfies the CR equation ux is equal to vy and uy is equal to minus vx. But this, from this, by definition, this definition, we obtain that v is harmonic conjugate of u. So by this way, this theorem is proved. Now let us see ML inequality. What is this statement says that let C denotes a contour of length L, and suppose that a function fz is piecewise continuous on C, and if m is non-negative constant such that modulus of fz is less than equal to m for all points z on C at which fz is defined, then modulus of integration of fz dz over C is less than equal to ml. So this we have to prove. So let us see the proof. Let z is equal to zt, a is less than equal to less than equal to b be a parametric representation of C. Then modulus of integration of fz dz over C, which is equal to modulus of integration fz dz into d z dash t dt from a to b, is less than equal to integration a to b modulus of fzt into z dash t dt. But modulus fzt into z dash t is equal to modulus fzt into z dash t, which is less than equal to m times modulus z dash t. This is because of this. So it follows that modulus of integration fz dz over c is less than equal to m using this one and this one, m into integration a to b modulus z dash t dt, which is equal to ml, where a to b modulus z dash t dt is equal to l, which is the length of contour C. Now let us see an example. Let C dot denote the circle z is equal to z naught plus r e to the power I theta, where theta lies in this interval. Use this parametric representation to show that integration dz upon z minus z naught over c naught is equal to 2 pi I. So let us see the solution. Let z is equal to z naught plus r e to the power I theta, which is given. So this implies dz is equal to I times r e to the power I theta d theta. So therefore the integration dz upon z minus z naught over c naught is equal to minus pi to pi I times r e to the power I theta d theta divided by r e to the power I theta. All these are cancelled and simplified form is I times minus pi to pi d theta, and this gives theta minus pi to pi, and this gives the value 2 pi I. So by this way we have proved that this integration is equal to 2 pi I. Now let us see Cauchy integral formula as a theorem. Let f is analytic everywhere inside and on a simple closed contour C. This is the first supposition taken in positive sense. Now if z0 is any point interior to C, then in f z0, that is the value of f at z0, is equal to 1 upon 2 pi I integration of fz upon z minus z0 dz over C. These two are equal. So this formula is called Cauchy integral formula, and if this formula Cauchy integral formula is written as integration over C fz dz upon z minus z naught is equal to 2 pi I fz naught, that is this multiplied over here, then it can be used to evaluate certain integrals along simple closed contour. So let us see the proof. Let C rho denote a positively oriented circle z minus z naught is equal to rho, where rho is small enough that C rho is interior to C. So this is the figure. Here C rho we have created or drawn, and z naught is the point as a center of the circle. Now since the quotient fz upon z minus z naught is analytic between and on the contour C rho and C, it follows from the principle of deformation of path that these two integrals are equal. That is fz upon z minus z naught dz over C is same as integration fz upon z minus z naught dz over C rho. Therefore, we are finding this expression integration over C fz dz upon z minus z naught minus fz naught into integration C rho dz upon z minus z naught, that will be equal to integration of over C rho fz minus fz naught upon z minus z naught dz. But integration dz upon z minus z naught over C naught C rho is equal to 2 pi I, that we have seen in last slide, and so the equation number 1, that is this equation, becomes integration over C fz dz upon z minus z naught minus 2 pi I z naught is equal to integration of fz minus fz naught upon z minus z naught over 0 dz. Now as f is analytic and therefore continuous at z naught, therefore for each epsilon greater than 0 there exists a delta greater than 0 such that modulus of fz minus fz naught is less than epsilon whenever z minus z naught is less than delta. This is because f is analytic and continuous. Because of this, this expression holds. Now let the radius rho of the circle C rho be smaller than the delta. Then on any point z on C rho, modulus z minus z naught is equal to rho. So we have by ML inequality integration modulus of integration fz minus fz naught upon z minus z naught over 0 is less than equal to C upon rho into 2 pi rho. C upon rho works as a m, and this is the length L. So this is equal to 2 pi epsilon. So we have from this equation we have that modulus of integration over C fz dz upon z minus z naught minus 2 pi I fz naught is less than equal to 2 pi epsilon. But as epsilon greater than 0 is arbitrary, we have integration over C fz dz upon z minus z naught is equal to 2 pi I fz naught. So by this way, this theorem is proved. Thank you very much. You can find the link of this PPT in description box. Thank you.